So this takes us to the concept of laminar and turbulent flows. So in general, in small velocities, in fact, as we have many times, we have what is called laminar flow. What is laminar flow? Look, laminar flow, typically, we can say that is when trajectories, path lines of the particles don't mix with each other. So we can have trajectories like that. I'm talking about trajectories, about path lines, or that is an object that is in a flow around an object. And you can also have vortices, so where the path lines are closed path lines like that. But you know, typically, no one mixes with the others, right? No one mixes with the others. And this is where our theory, typically the equations that we have developed for fluid mechanics, the Navier-Stokes equations are valid for. Otherwise, they are not. This is quantified. How do we quantify slow motion, so a laminar flow, laminar clamps for the fact that we are moving in a shallow way, right? So, or how do we quantify that? Well, there is a classical number that is very familiar for fluid mechanics people. It's the Reynolds number. The Reynolds number is a number which is proportional to the velocity. What velocity? Well, a representative velocity of all the velocities in the domain that we are studying, the size of the domain that we are studying, and inversely proportional to the viscosity of the fluid. In reality, that is what is called the kinematic viscosity, which is the really mu viscosity divided by rho. Okay? So look, that number can be obtained for every problem. When this number is small, then the smaller is this number, the more laminar tends the motion to be. Okay? So that means that for small velocities, when the velocity is very small, then of course this number is small. Whenever there is some viscosity. But even for small velocities, for relatively regular velocities, if the viscosity is very, very, very small, then this Reynolds number is very large, could be large. Okay? So this typical, I'm not extending my dissertation on that, I just let you know that there is this Reynolds number, whenever it's of the order of hundreds, or smaller, then our theories are applicable, okay? Which is most of cases. For instance, in our design of canals, our designs of pipes, our design of spillways. You know what spillways are in dams? Huh? The aliviaderos, okay? So there is a typical laminar flow. Doesn't mean that the velocity can be the velocity large, okay? The velocity can be large, but the whole value of that is small. There are other situations in which this is not the case. Typically, in our cases, is at the end of the spillways. Sometimes there are placed some devices to break the energy of that. So this cannot be modeled. This is modeled essentially with empirical models, and this cannot be considered a laminar flow. But most of our designs, the canals, the dams, the spillways, the pipes, are based and are amenable to be modeled by laminar flow. But it's important that you know that there is another life. For instance, aeronautics engineers that work with air as a fluid. Air is a low viscosity fluid, and in an engine that is flying around the wings or whatever, the velocity of the air is very large. So the Reynolds number can be very large. And then we enter in another world. What is the other world? That is the turbulent flow. So laminar flow is the one that we use, and it's characterized by that. No? The motion of the particles tend to be in parallel for different particles. Okay? And also the velocities along time are smooth. They can vary, they can be high or low, but they are smooth. But as the Reynolds numbers increases, and go beyond that, what happens is that the fluid becomes turbulent. What is that noticed by? You know, maybe you have had this opportunity. As the fluid is transparent, is accelerated very much, it becomes less transparent. Okay, so the optical properties of the fluid are changed by the fact that a turbulent flow is onsetting in that fluid, and that's characterized by that. Now the velocities at every particle are rapidly, extremely rapidly fluctuating around some mean values. But the real velocities are really high, but fluctuating from that side. So imagine particles fluctuating that way and moving a long time along some. But of course, then Navier-Stokes equations are not applicable. The behavior of the fluid is no longer Newtonian. So this can be studied. That is normally called turbulent flow, and then it needs an additional theory for that. Okay, and also much more complex theories, and then requires also for computational mechanics issues many complex models, which in turn requires very highly computational cost analysis. Okay.